In the final years of the 19th century, the edifice of classical physics seemed nearly complete. The laws of motion laid down by Newton beautifully described the orbits of the planets, while Maxwell's equations had unified electricity, magnetism, and light into a single, elegant framework. There was a prevailing sense among many physicists that the great work was done, and all that remained was to refine measurements to ever greater degrees of precision. Yet, in the quiet corners of laboratories, a few persistent, troublesome clouds were gathering on the horizon, refusing to dissipate under the bright sun of classical theory. One of the most stubborn of these clouds was the problem of black-body radiation. The term sounds esoteric, but the concept is quite ordinary. A black body is an idealized object that absorbs all radiation that falls upon it, and when heated, it glows, emitting radiation of its own across a range of frequencies. Think of a piece of iron in a blacksmith's forge, glowing first red, then orange, then yellow-white as it gets hotter. Physicists wanted to create a formula that could predict the intensity of light emitted at each frequency, based only on the object's temperature. Classical theories provided a prediction, but it failed spectacularly. The existing formulas worked well for low frequencies, but they predicted that as the frequency increased into the ultraviolet range, the energy emitted should become infinite. This nonsensical result was dubbed the ultraviolet catastrophe, a clear sign that something was deeply wrong with the fundamental understanding of how energy and matter interacted.
It was a German physicist named Max Planck who, in the year 1900, reluctantly offered a solution. He was a conservative physicist, deeply invested in classical thermodynamics, and he approached the problem not with a revolutionary spirit, but with a sense of quiet desperation. After exhausting all conventional avenues, he tried what he later called an act of despair. He introduced a strange mathematical trick into his equations. He proposed that the energy of the light waves could not be emitted or absorbed in a continuous, smooth flow. Instead, he suggested it could only be exchanged in discrete, tiny packets, or chunks. He called these packets quanta. The size of each energy packet, he proposed, was directly proportional to the frequency of the radiation. This single, seemingly arbitrary assumption miraculously solved the problem. His new formula perfectly matched the experimental data at all frequencies, and the ultraviolet catastrophe simply vanished. Planck himself was deeply unsettled by his own discovery. He viewed the idea of energy quanta as a purely formal assumption, a mathematical contrivance that happened to work, but which likely had no deep physical meaning. He spent years trying to fit his formula back into a classical framework, to no avail. He had, almost against his will, opened a door into a new reality, one where energy was not a continuous stream, but a grainy, pixelated quantity. He had laid the first stone of quantum mechanics, even if he did not yet recognize the foundation he was building.
5 years later, in 1905, a young and still unknown patent clerk in Bern, Switzerland, took Planck's idea far more seriously. Albert Einstein, in one of his 4 revolutionary papers published that year, turned his attention to another unexplained phenomenon, the photoelectric effect. It had been observed that when light shines on a metal surface, it can knock electrons loose. Curiously, the ability of the light to dislodge these electrons did not depend on the light's brightness, but on its color, or more precisely, its frequency. A dim blue light could eject electrons, while an intensely bright red light could not. This made no sense from a classical wave perspective, where a brighter, more energetic wave should have more of an impact.
Einstein saw the answer in Planck's quanta. He made the radical proposal that Planck's idea was not just a mathematical trick related to how energy is absorbed or emitted, but a fundamental property of light itself. He suggested that light itself is composed of these discrete particles of energy, which were later named photons. A photon of blue light, having a higher frequency, carries more energy than a photon of red light. An electron is knocked loose only when it is struck by a single photon carrying enough energy to overcome the forces binding it to the metal. A brighter light simply means more photons are arriving, but if each individual photon is too weak, like those of red light, then no electrons will be ejected, no matter how many photons strike the surface.
With this insight, Einstein transformed Planck's hesitant hypothesis into a bold new theory about the very nature of light. Reality, it seemed, was quantized at its most fundamental level.
While the nature of light was undergoing this revolution, another mystery was brewing at the heart of matter itself, the structure of the atom. In 1911, Ernest Rutherford's experiments had revealed that the atom was mostly empty space, with a tiny, dense, positively charged nucleus at its center, orbited by negatively charged electrons. This planetary model was intuitive, but it had a fatal flaw according to classical physics. An orbiting electron is an accelerating charge, and Maxwell's equations clearly stated that any accelerating charge must radiate electromagnetic energy. This constant loss of energy should cause the electron to rapidly spiral inward, collapsing into the nucleus in a fraction of a second. By the logic of classical physics, atoms should not be stable. The fact that the chair you are sitting on and you yourself exist at all was a profound puzzle.
The solution came from a Danish physicist named Niels Bohr, who had come to work with Rutherford in Manchester. In 1913, Bohr proposed a new model of the atom that audaciously blended classical physics with the new quantum ideas. He put forward a set of postulates. First, he stated that electrons could only exist in certain specific stable orbits around the nucleus, each with a fixed energy level. While in one of these allowed orbits, an electron simply did not radiate energy, in defiance of classical laws. Second, he proposed that an electron could jump from a higher energy orbit to a lower one, and in doing so, it would emit a single photon of light. The energy of this photon, and therefore its color, was precisely equal to the energy difference between the two orbits. This model explained with stunning accuracy the mysterious spectral lines of hydrogen, the specific discrete colors of light that hydrogen gas emits when energized. It was as if atoms had a unique barcode written in light, and Bohr's model had finally deciphered it.
Bohr's model was a monumental success, but it was also deeply strange. It was a hybrid, a patchwork of old and new rules that worked, but lacked a coherent underlying principle. It answered the what, but not the why. Why were only certain orbits allowed? The next piece of the puzzle came from an unlikely source, a young French prince named Louis de Broglie. In his 1924 doctoral thesis, de Broglie put forth a simple but profound idea. He had been contemplating the dual nature of light, which sometimes behaved like a wave and sometimes like a particle. He wondered if this duality might be a universal principle. If waves can act like particles, he reasoned, then perhaps particles, like electrons, can act like waves. He proposed that every moving particle has a wavelength associated with it, a wavelength that is inversely proportional to its momentum.
This idea was so strange that the examiners of his theses were unsure what to make of it, and they sent it to Einstein for his opinion. Einstein recognized its potential immediately, and de Broglie was awarded his doctorate. The idea that electrons could be waves provided a beautiful explanation for Bohr's mysterious orbits. An electron could only exist in an orbit where its associated wave could fit perfectly around the nucleus, forming a stable standing wave pattern, much like the vibrations of a guitar string. Orbits where the wave would not close on itself would interfere destructively and could not persist. The quantum conditions were no longer arbitrary rules, but a natural consequence of the electron's wave nature. De Broglie's hypothesis was theory, but just a few years later, experiments confirmed that a beam of electrons could indeed be diffracted, a hallmark behavior of waves. The wave-particle duality was not just a feature of light, but a fundamental characteristic of all matter.
This wave-like nature of matter required a new kind of mechanics. The old Newtonian picture of particles as tiny billiard balls following precise trajectories was clearly inadequate. In 1926, the Austrian physicist Erwin Schrödinger developed a mathematical equation that became a cornerstone of the new physics. The Schrödinger equation describes the behavior of de Broglie's matter waves over time. The solution to this equation is a mathematical entity called a wave function, represented by the Greek letter psi. The wave function for an electron in an atom, for instance, doesn't describe a definite path, but rather a cloud of probability. The wave is not a physical wave in the sense of a water wave, but a wave of information. The density of the wave at any given point in space corresponds to the probability of finding the particle at that location if one were to look for it. The electron is no longer in a single place, but exists as a smear of potentiality, a superposition of all possible positions until a measurement is made.
At almost the same time, a young German physicist named Werner Heisenberg developed an entirely different mathematical formulation of quantum mechanics. His approach, called matrix mechanics, was more abstract and did not rely on a wave picture. It dealt only with observable quantities, like the energy and momentum of particles, which he represented in arrays of numbers called matrices. It was soon proven that Schrödinger's wave mechanics and Heisenberg's matrix mechanics were mathematically equivalent. They were two different ways of describing the same bizarre quantum reality. From his work, Heisenberg also derived one of the most famous and unsettling principles of the new physics. The Heisenberg uncertainty principle states that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle can be known simultaneously. For instance, the more precisely you measure the position of an electron, the less precisely you can know its momentum, and vice versa. This is not a limitation of our measuring instruments. It is an inherent, inescapable fuzziness built into the fabric of nature itself. The classical dream of a clockwork universe, where knowing the position and velocity of every particle would allow one to predict the future with perfect certainty, was gone forever. Reality, at its finest scale, was a world of probabilities, uncertainties, and echoes of potential.
The establishment of this new quantum framework, with its wave functions and uncertainty, presented a profound challenge, not just to physics, but to the very concept of reality itself. Physicists were confronted with a set of mathematical rules that provided astonishingly accurate predictions, but seemed to describe a world that defied all common sense. The question of what the mathematics truly meant, what it was telling us about the world when we are not looking at it, became the subject of intense and sometimes acrimonious debate. The dominant interpretation, which coalesced around Niels Bohr and his institute in Copenhagen, became known as the Copenhagen interpretation. At its heart was a radical proposition that it is meaningless to speak of the properties of a quantum object, such as an electron's position or momentum, before a measurement is made. Before the act of observation, the electron does not have a definite position. It exists only as a wave function, a cloud of probabilities, a superposition of all possible outcomes. The act of measurement forces the system to choose one of these possibilities, causing the wave function to instantaneously collapse into a single definite state.
This idea of a measurement-induced collapse was deeply troubling. It seemed to grant a special, almost mystical role to the act of observation. What precisely constituted a measurement? Did it require a human consciousness, or could a simple, inanimate detector suffice? And how did this collapse happen? The Schrödinger equation described the smooth, continuous evolution of the wave function, but the collapse was a sudden, discontinuous jump that was not described by the equation itself. It was as if two different sets of rules governed the universe, one for the quantum world when it is left alone, and another for the moment it interacts with the macroscopic world of our experience. This division, known as the Heisenberg cut, was arbitrary and unsatisfying. To highlight the philosophical absurdity he saw in this interpretation, Erwin Schrödinger conceived of a famous and macabre thought experiment. He imagined a cat placed inside a sealed, opaque box. Alongside the cat is a diabolical device, a single radioactive atom, a Geiger counter, a hammer, and a vial of poison. The setup is arranged so that if the atom decays, an event governed by the probabilistic laws of quantum mechanics, the Geiger counter will detect it, triggering the hammer to smash the vial, releasing the poison, and killing the cat.
According to quantum mechanics, after a certain amount of time, the radioactive atom is in a superposition of two states. It has both decayed and not decayed.
If the atom is in a superposition and the fate of the cat is directly linked to the state of the atom, then it follows that the entire system inside the box must also be in a superposition. The cat, according to a strict application of the Copenhagen interpretation, is therefore simultaneously both alive and dead, its wave function a perfect 50-50 mix of these two contradictory states. It is only when an observer opens the box to check on the cat that the wave function collapses and reality is forced to choose one outcome. The cat is then found to be definitively either alive or dead. Schrödinger did not believe in the existence of a half-dead, half-alive cat. His purpose was to demonstrate the paradoxical and seemingly nonsensical consequences of applying the rules of quantum superposition, which work so well for atoms and electrons, to a large-scale, everyday object like a cat. The thought experiment starkly illustrates the measurement problem. Where does the quantum world end and the classical world begin? And what is the true nature of the transition between them?
While Schrödinger used paradox to question the new orthodoxy, Albert Einstein mounted a more direct and persistent challenge, fueled by a deep-seated philosophical conviction. He could not accept that the fundamental nature of reality was based on chance and probability. His famous declaration that God does not play dice encapsulated his belief that quantum mechanics, for all its predictive success, must be an incomplete theory. He believed there must be a deeper, more deterministic reality hidden from view. He imagined that particles like electrons always have definite properties, such as position and momentum, even when they are not being measured. The uncertainty and probability of quantum mechanics, in his view, simply reflected our ignorance of these underlying hidden variables. This led to a series of long and thoughtful debates between Einstein and Bohr, two giants of physics, arguing over the very soul of their discipline. They debated in private and in public, at conferences and through publications, each trying to convince the other with ever more ingenious thought experiments.
The most powerful of these challenges came in 1935, in a paper co-authored by Einstein with his colleagues Boris Podolsky and Nathan Rosen. The argument, now known as the EPR paradox, was not designed to prove quantum mechanics wrong, but to show that it must be incomplete. It focused on a peculiar quantum phenomenon called entanglement. It is possible to create two particles, such as photons or electrons, in such a way that their properties are intimately linked, no matter how far apart they travel. For instance, one could create two electrons whose total spin is zero. Spin is a quantum property, and for an electron, it can be measured as either up or down along any chosen axis. If the total spin is zero, it means that if one electron is measured to have spin up, the other must instantly be found to have spin down, and vice versa. They are forever correlated.
The thought experiment imagines creating such a pair of entangled electrons and then sending them in opposite directions across the galaxy. After they have traveled for many light years, an observer, let's call her Alice, measures the spin of her electron along a particular axis. Let's say she finds it to be spin up. According to quantum mechanics, she instantly knows that the other electron, now light years away and measured by her colleague Bob, will be found to have spin down if he measures it along the same axis. Herein lies the paradox. According to the Copenhagen interpretation, before Alice's measurement, neither electron had a definite spin. It was the act of her measurement that collapsed the wave function and forced her electron into the spin-up state. But this collapse also seemed to instantaneously affect Bob's electron, light years away, forcing it into the spin-down state. This instantaneous influence, seemingly traveling faster than the speed of light, was what Einstein derisively called spooky action at a distance. Since the theory of relativity forbids any signal or influence from traveling faster than light, Einstein argued that this was impossible.
The only way to avoid this spooky action, Einstein, Podolsky, and Rosen contended, was if the particles had definite properties all along. The outcome of Alice's measurement was not determined at the moment she made it, but was predetermined from the moment the particles were created. The spin of each electron was a hidden variable, an element of reality that quantum mechanics was failing to describe. The particles were like a pair of gloves separated at birth and sent to opposite ends of the Earth. If you open your box and find a left-handed glove, You know instantly that the other box contains a right-handed glove. There is no spooky action. The information was there all along. For decades, this remained a philosophical debate. It seemed impossible to design an experiment that could distinguish between Bohr's view of an indeterminate reality with spooky connections and Einstein's view of a predetermined reality that just looked random. The debate was about the nature of reality when it is not being observed, and it seemed fundamentally untestable.
Then, in the 1960s, a brilliant and unassuming Irish physicist named John Stuart Bell found a way to take the argument out of the realm of philosophy and into the laboratory. He devised a remarkable mathematical theorem, now known as Bell's theorem. He demonstrated that if Einstein's worldview, a combination of locality, no spooky action at a distance, and realism, particles have definite properties even when unobserved, were true, then the correlations between measurements performed on entangled particles by Alice and Bob would have to obey a certain mathematical constraint, an inequality. Bell showed that you could set up an experiment where Alice and Bob each randomly choose to measure the spin of their particles along one of several different angles. If reality is local and predetermined, as Einstein believed, there is a limit to how strongly the results of their independent measurements can be correlated.
Crucially, Bell also calculated what quantum mechanics would predict for the same experiment. He found that the correlations predicted by quantum theory would be stronger than the limit imposed by Einstein's local realism. Quantum mechanics predicted a violation of Bell's inequality. This was a profound breakthrough. Bell had translated a philosophical debate about the nature of reality into a concrete, testable prediction. The question could now be settled by experiment. One could create pairs of entangled particles, send them to distant detectors, perform the measurements along different angles, and see if the results obeyed the inequality of local realism or violated it, as predicted by quantum mechanics. The experiments were extraordinarily difficult to perform, requiring incredible precision and the ability to measure the properties of single photons or atoms.
Starting in the 1970s and continuing with increasing sophistication, physicists began to conduct these tests. The most famous of the early experiments were performed in the early 1980s by a team led by the French physicist Alain Aspect. His experiments used pairs of entangled photons. The results were clear and unambiguous. Over and over again, the experiments showed a violation of Bell's inequality. The correlations between the distant particles were stronger than could ever be explained by any local, predetermined theory. The results were exactly in line with the predictions of quantum mechanics. Einstein's intuition, as powerful and logical as it seemed, was wrong. The universe does not obey local realism. The spooky action at a distance, it turned out, was real. This experimental verification has been repeated many times since, with ever-improving technology closing potential loopholes in the experimental design. The conclusion remains unshaken. The world, at its most fundamental level, is non-local. The fate of two entangled particles can be intrinsically linked, forming a single indivisible system even when separated by vast distances. Measuring one part of this system can instantaneously influence the other part in a way that defies our classical understanding of space and separation. This does not mean that we can send information faster than light. A careful analysis shows that the inherent randomness of the quantum measurements prevents this. But it does mean that the universe is interconnected in a way that is far deeper and stranger than classical physics could ever have imagined. The echoes of a single quantum event can reverberate across the cosmos, binding the fabric of reality together in a subtle, ghostly embrace. The world of definite objects, clearly separated in space and time, is merely a large-scale approximation of a much more holistic and interconnected quantum reality.
The stark experimental verdict against local realism did not, however, automatically vindicate the Copenhagen interpretation. While its predictions about the correlations were correct, the fundamental unease surrounding the measurement problem and the collapse of the wave function remained. The confirmation of non-locality simply deepened the mystery, closing one avenue of escape proposed by Einstein, but leaving the central questions unanswered.
If the universe was indeed spooky, what was the nature of this spookiness, and how did it give rise to the solid, definite, and decidedly unspooky classical world of our everyday experience? The search for a more complete and coherent picture of quantum reality led physicists down several divergent and conceptually radical paths, each attempting to build a consistent narrative from the strange clues provided by experiment.
One of the most audacious and mind-bending of these alternatives was first proposed in the 1950s by a young graduate student at Princeton named Hugh Everett III. Everett was troubled by the same issues that bothered Schrödinger and Einstein: the arbitrary division of the world into a quantum system and a classical observer, and the discontinuous jump of the wave function collapse, which was postulated by the Copenhagen interpretation but not described by the fundamental Schrödinger equation. Everett's radical proposal was to simply take the Schrödinger equation at its word and apply it universally, to everything, at all times. In his view, the wave function never collapses. Instead, every time a quantum measurement is made, or more generally, any time a quantum system in a superposition interacts with a larger system, the entire universe branches. The superposition is not resolved into one outcome. Rather, all possible outcomes of the measurement actually occur, each in its own separate parallel universe.
Let us return to Schrödinger's unfortunate cat. According to Everett's formulation, which would later be known as the many worlds interpretation, when the radioactive atom enters a superposition of decayed and not decayed, the universe itself splits into two distinct branches. In one branch of the universe, the atom has decayed, the poison has been released, and the cat is dead. In the other branch, the atom has not decayed, the poison remains secure in its vial, and the cat is alive. When an observer opens the box, they too become part of this entanglement and branching. The observer's wave function splits, with one version of the observer finding a dead cat in one universe and another version of the same observer finding a living cat in a parallel universe. From the perspective of each observer within their own branch, it appears as though the wave function has collapsed to a single outcome, but this is merely an illusion of perspective. In the larger reality, which Everett called the multiverse, all possibilities encoded in the initial wave function have been realized.
This interpretation elegantly solves the measurement problem by eliminating the need for a collapse postulate. The Schrödinger equation governs all evolution, smoothly and deterministically. There is no special role for measurement or consciousness, and there is no arbitrary cut between the quantum and classical worlds. The entire universe is a single, vast quantum system. However, it achieves this mathematical consistency at the cost of a truly staggering ontological extravagance. It requires us to accept the existence of a near infinite number of parallel universes, constantly splitting and branching with every quantum interaction, each one as real as our own. We are completely unaware of these other worlds and our other selves, as they no longer interact or interfere with our branch of reality once the split has occurred. For many physicists, this proliferation of unseen worlds was too high a philosophical price to pay, a violation of the principle of Occam's razor, which favors simpler explanations.
A very different approach to resolving the quantum mystery sought to restore a sense of objective reality, not by multiplying worlds, but by adding to the existing theory. This idea, known as the de Broglie-Bohm theory or pilot wave theory, actually predates many of the other interpretations, having been first proposed by Louis de Broglie in the 1920s, and later rediscovered and developed by David Bohm in the 1950s. Like Einstein, Bohm was deeply dissatisfied with the Copenhagen interpretation's denial of an underlying reality. His theory posits that particles, such as electrons, are indeed real particles that always have a definite, precise position even when we are not looking at them. There is no fundamental uncertainty about where things are. The strangeness of quantum mechanics, in this view, arises not from the particles themselves, but from the fact that they are always accompanied by a guiding wave or a pilot wave. This pilot wave is described by the Schrödinger equation and permeates all of space. It acts as a sort of information field that guides the motion of the particles, much like a current in a river guides a piece of driftwood. The wave can go through both slits in a double slit experiment, creating an interference pattern, and the particle, being guided by the wave, is naturally directed towards the bright fringes of the pattern and away from the dark fringes. All of the probabilistic nature of quantum mechanics is therefore explained not as a fundamental indeterminacy in reality, but as a result of our ignorance of the particle's precise initial position within its guiding wave. This picture is fully deterministic. If you knew the exact position of the particle and the state of its pilot wave, you could predict its future trajectory with perfect certainty. The theory cleverly avoids the constraints of Bell's theorem because it is explicitly non-local. The pilot wave extends through space, and a change in the wave in one location, caused by a measurement on one entangled particle, for instance, can instantaneously affect the shape of the wave everywhere, thus influencing the trajectory of another particle light years away. It sacrifices locality to preserve a deterministic, objective reality.
While the many worlds and de Broglie-Bohm interpretations offer grand, all-encompassing narratives about the ultimate nature of reality, a third, more pragmatic development in quantum physics provided a crucial piece of the puzzle without necessarily committing to a single philosophical worldview. This development is the theory of quantum decoherence. It doesn't claim to be a full interpretation itself, but it provides a physical explanation for why the classical world appears classical, and why we do not perceive macroscopic superpositions in our daily lives. The central insight of decoherence is that no quantum system is ever perfectly isolated from its environment. Schrödinger's cat is not alone in its box. It is constantly interacting with billions upon billions of air molecules, photons of light, and the atoms of the box itself. Each of these microscopic interactions constitutes a kind of measurement. When the cat is in a superposition of alive and dead, this quantum state very quickly becomes entangled with the states of all the surrounding environmental particles. An air molecule bouncing off the living cat will recoil differently than one bouncing off the dead cat. A photon of heat radiated by the living cat will carry different information than one from the dead cat. The information about the superposition, the delicate phase relationship between the alive and dead states, leaks out with breathtaking speed into the surrounding environment, becoming hopelessly scrambled and distributed across an impossibly vast number of particles. This process, the rapid entanglement of a system with its environment, is decoherence.
The practical effect of decoherence is the suppression of quantum interference. The two branches of the cat's wave function, alive and dead, can no longer interfere with each other because they are now each tied to a completely different and overwhelmingly complex state of the environment. For any observer, including the particles of the environment themselves, it is as if the wave function has collapsed. The system now behaves, for all intents and purposes, like a classical statistical mixture of two possibilities, not a quantum superposition of both. Decoherence explains why we only ever see a live cat or a dead cat, not a ghostly blend of the two. The environment itself acts as a vast and persistent observer, constantly measuring the system and forcing it to behave in a classical manner. This mechanism is now a well-understood and experimentally verified part of physics, and it has become central to modern thinking about the quantum to classical transition. It provides a physical basis for the Heisenberg cut that the Copenhagen interpretation had to impose by decree. Proponents of the many worlds interpretation see decoherence as the mechanism that governs the splitting of the universe. The different states of the environment define the separate, non-interfering branches. For proponents of other interpretations, decoherence simply explains why the world appears to collapse without solving the ultimate question of whether it truly does. It transforms a superposition into a set of classical alternatives, but it does not, on its own, select one of those alternatives to be the single reality we experience. The puzzle remains, but decoherence has sharpened its focus, showing us that the emergence of the classical world from the quantum substrate is not a mystical act of consciousness, but a physical process driven by the relentless, dissipative interactions between a system and its surroundings. The search for meaning in quantum mechanics continues, no longer a simple two-sided debate between Bohr and Einstein, but a rich and complex exploration of multiple possible realities, each consistent with the strange echoes that our experiments have detected.
Beyond the proliferation of worlds or the guidance of hidden waves, another family of theories confronts the measurement problem head-on by proposing that the Schrödinger equation is not, in fact, the complete story. These models, known as objective collapse theories, suggest that the elegant, linear evolution of the wave function is occasionally and spontaneously interrupted by a fundamentally new physical process, a genuine objective collapse. Unlike in the Copenhagen interpretation, this collapse is not triggered by a conscious observer or a special measurement device. Instead, it is a random, unpredictable event that is a built-in feature of nature, happening to all quantum systems, everywhere, all the time. The most well-known of these is the Ghirardi-Rimini-Weber theory, or GRW, developed in the 1980s. The GRW model modifies the Schrödinger equation by adding a nonlinear, stochastic term that describes this collapse process.
According to GRW theory, every elementary particle in the universe has an exceedingly small, constant probability in any given moment of spontaneously undergoing a localization. When this happens, its diffuse wave function, which might have been spread over a large region of space, abruptly and randomly contracts to a very specific narrow location. The chance of this happening to any single isolated particle is astronomically low, perhaps once in 100 million years. For a single electron in a superposition, it would likely maintain its quantum nature for an eon, evolving according to the standard Schrödinger equation without interruption. However, the true power of the theory becomes apparent when considering macroscopic objects. A cat, a Geiger counter, or even a dust mote is composed of an immense number of particles, on the order of trillions of trillions. Because the collapse process is random for each particle, the probability that at least one particle within the macroscopic object will undergo a collapse in any tiny fraction of a second is virtually 100.
Due to the nature of quantum entanglement, all the particles that make up the cat are linked together in a single collective wave function. The moment a single one of these particles spontaneously localizes, the entire entangled system is forced to collapse with it. If the cat is in a superposition of alive and dead, this state is linked to the positions of all the atoms in its body. A spontaneous localization of just one of those atoms to a position consistent with the alive state will instantaneously collapse the entire cat into the alive state. The same is true for the dead state. Therefore, a macroscopic object like a cat simply cannot exist in a superposition for any meaningful length of time. The sheer number of its constituent particles guarantees an almost instantaneous collapse into a definite classical state. The theory thus provides a physical mechanism that explains the divide between the microscopic and macroscopic worlds without appealing to observers or measurement. It accomplishes this by introducing two new fundamental constants of nature: the rate at which collapses occur for a single particle, and the degree of spatial localization that a collapse produces. A significant appeal of objective collapse models is that they are, in principle, experimentally testable. The spontaneous collapses they propose are not perfectly silent. They should produce a tiny amount of energy, leading to a very slight constant heating of all matter. Experiments are currently underway to detect this predicted effect, searching for a deviation from standard quantum mechanics that could signal a deeper, more active reality.
Moving in a completely different philosophical direction, some physicists and philosophers have argued that the conceptual difficulties of quantum mechanics arise from a mistaken view of the wave function itself. This perspective, known as quantum Bayesianism or cubism, proposes a radical reinterpretation of what the quantum state represents. In cubism, the wave function associated with a physical system does not describe an objective property of that system, like its mass or charge. Instead, the wave function is purely a mathematical tool that represents the subjective degrees of belief or credence that a particular agent holds about the probable outcomes of their future interactions with that system. It is a tool for managing uncertainty, an expression of information held by an observer rather than a direct representation of an external reality. From this viewpoint,
The infamous collapse of the wave function is not a real physical process that happens out in the world. It is simply the process of an agent updating their beliefs in light of new information. Before you open Schrödinger's box, your wave function for the cat reflects your uncertainty, assigning a 50% probability to both the alive and dead outcomes. This wave function represents your state of knowledge. When you open the box and see a living cat, you gain new information. Consequently, you update your beliefs, and your wave function for the cat changes discontinuously to one that assigns 100% probability to the alive state. The collapse happened only in your mind, a Bayesian update of probability based on new data. There is no paradox, because the wave function was never an objective thing that needed to physically collapse in the first place.
Cubism dissolves the measurement problem by personalizing it. The outcome of a quantum measurement is an experience for the agent who makes it. The world does not split, nor does a particle get guided by a hidden wave. Rather, an agent interacts with the world and, in doing so, creates a new experience for themselves, updating their internal model of reality accordingly. This means that wave functions are specific to each agent. You have your wave function for an electron, and I have mine. They will likely be similar if we have similar information, but they are not the same thing, and neither is the true wave function of the electron. The theory rejects the traditional third-person, God's eye view of science, where the goal is to describe a single, objective reality that exists independently of us. Instead, Cubism suggests that quantum mechanics is a first-person theory, a user's manual for navigating a world that is fundamentally indeterminate, where our actions play a genuine role in bringing about definite outcomes. It offers a picture of a participatory universe, where reality is not just passively observed, but actively shaped through our interactions with it.
A related, though distinct, interpretation that also challenges the notion of an absolute, observer-independent reality is relational quantum mechanics, or RQM, developed by the physicist Carlo Rovelli. Inspired by the way Einstein's theory of special relativity revealed that concepts like time and space are relative to an observer's frame of reference, RQM proposes that the state of a quantum system is also relative. A system's properties, such as its position or spin, are not intrinsic to it. Instead, a property only becomes definite in the context of an interaction between that system and another system, which can be called the observer. In RQM, any physical system can be an observer for any other physical system. There is no absolute, universal state of the world. There are only the states of systems relative to other systems.
To illustrate, consider an electron with an uncertain spin. According to RQM, it is meaningless to ask what the electron's spin really is in isolation. If you, as an observer, measure the spin, you might find it to be up. In that interaction, the electron's spin has become definite relative to you. It now has the property of spin up with respect to you. Now imagine a second observer, your friend, who does not interact with the electron, but only observes you and your measurement apparatus. From your friend's perspective, before they communicate with you, you and the electron have become entangled. Relative to your friend, you are now in a superposition of having seen spin up and having seen spin down. Both descriptions are correct from their respective relational viewpoints. Your reality, in which the spin is definitely up, is valid. Your friend's reality, in which you are in a superposition, is also valid. The apparent contradiction is resolved when your friend interacts with you, perhaps by you telling them the result. At that moment, the state of the electron and your state becomes definite relative to your friend as well.
This framework dissolves the measurement problem by removing the concept of a single objective state that needs to collapse. A measurement is just an interaction like any other, which establishes a correlation or a set of relative facts between the two interacting systems. The world is thus described as a network of relations, a web of physical interactions where properties are only manifested at the points of contact. There is no view from nowhere. RQM offers a coherent worldview that is deeply non-local, but avoids the ontological baggage of many worlds or hidden variables. It suggests that the strangeness of quantum mechanics
is a consequence of our attempt to impose an outdated absolute view of reality onto a world that is fundamentally relational. It asks us to accept that the physical world may not have a single universal story, but rather a multitude of partial stories, each one told from the perspective of a particular system within it.
Yet, if the properties of the world are only defined through these pairwise interactions, a profound question arises concerning the solidity of our shared reality. If your facts about an electron are relative to you, and my facts are relative to me, why do we so consistently find ourselves agreeing on the state of the world around us? An elegant and increasingly influential idea, known as quantum Darwinism, developed primarily by the physicist Wojciech Zurek, attempts to answer this very question by explaining how a stable, objective, classical reality can emerge from the underlying quantum foam. The theory does not modify quantum mechanics, but instead closely examines the role of the environment, a factor that is often treated as a mere source of noise to be isolated and ignored. In quantum Darwinism, the environment is elevated to the central actor in the creation of classicality. The core insight is that certain quantum states are far more robust and stable than others when interacting with a vast, messy environment. These preferred states, called pointer states, are the ones that are able to survive the relentless scrutiny of their surroundings.
Imagine a quantum system, such as an atom, that can have its spin pointing in many different directions at once. When this atom interacts with its environment, a flood of air molecules, photons, and other particles, most of its delicate superposition states are destroyed almost instantly through a process called decoherence. However, the pointer states, perhaps spin up and spin down, are special. They are the states that remain stable and do not get scrambled by the environmental interactions. Quantum Darwinism proposes that the environment does more than just select for these stable states, it actively creates and broadcasts information about them. As particles from the environment bump into and scatter off our central atom, they each carry away a small fragment of information about its pointer state. One photon might register that the spin is up. A nearby air molecule might get nudged in a way that is consistent with the spin being up, and so on. The environment effectively becomes a vast, redundant recording medium containing countless partial copies of the information about the system's stable state.
This massive proliferation of information is the key to objective reality. Many different observers can now independently probe small fractions of the environment to learn the state of the central system. You might intercept a few photons, I might analyze the motion of some gas molecules, and a third person might check a different portion of the environment altogether. Because the environment holds a colossal number of these information-carrying imprints, we can all find out the spin of the atom without directly disturbing it, and, more importantly, without ever having to communicate with each other. We will all arrive at the same conclusion because we are all reading from the same grand, publicly broadcasted message. Objectivity, in this view, is not a fundamental property of the world, but an emergent one. A fact becomes objective when it is recorded so redundantly in the environment that it is accessible to any number of observers. The classical world we perceive is therefore the set of fittest quantum states that have been selected for their robustness and whose existence has been advertised everywhere by a Darwinian-like process of informational survival and replication.
While quantum Darwinism offers an explanation for how a consensus reality can emerge from quantum interactions, another class of interpretation seeks to describe the very mechanism of the quantum event itself, viewing it not as a collapse or a branching, but as a completed negotiation across time. This is the transactional interpretation of quantum mechanics, proposed by John Cramer in the 1980s. It draws its inspiration from the Wheeler-Feynman absorber theory of electrodynamics, which treats electromagnetic waves symmetrically in time. The interpretation paints a startlingly literal picture of a quantum event, such as an atom emitting a photon that is later absorbed by a detector. According to this model, the emitting atom does not simply send a particle out into the void. Instead, it generates an offer wave, which is the standard wave function described by the Schrödinger equation, rippling forward in time. This wave travels outward, exploring all possible paths, passing through both slits in an experiment, and eventually reaching every potential absorbing particle in its future.
Each potential absorber, upon receiving this offer wave, is stimulated to respond. It generates a confirmation wave, which is a solution to the same wave equation, but one that travels backward in time, from the future back to the past. This confirmation wave retraces the path of the offer wave, arriving back at the emitter at the precise moment of emission. The emitter then feels all the confirmation waves returning from all the potential absorbers. A transaction, a handshake across space-time, is then selectively established with just one of these absorbers, the one whose confirmation wave arrives with the strongest amplitude. The exchange of energy and momentum, the event we perceive as a particle traveling from one point to another, is the completion of this transaction. All other potential transactions fade away. The actualized event is the result of a temporal dialogue between the past and the future.
This model provides a compellingly intuitive, if strange, explanation for many quantum puzzles. The phenomenon of non-locality in an entanglement experiment, for instance, is no longer mysterious. The transaction between two entangled particles is a single atemporal handshake that spans the distance between them, establishing their correlated properties outside of ordinary forward-moving time. There is no need for a signal to travel faster than light because the connection is already formed by the crisscrossing of offer and confirmation waves. In the double-slit experiment, the offer wave physically passes through both slits, exploring both paths. It reaches the detector screen, which sends confirmation waves back in time from all points. The locations on the screen where a particle is likely to land are where the offer and confirmation waves reinforce each other, and the transaction is completed. The wave function collapse in this view is not a sudden, mysterious process, but simply the moment the transaction becomes real, the handshake is sealed, and a single, definite history is chosen from among all the possibilities explored by the initial offer. It replaces the passive observer with an active dialogue between emitters and absorbers, weaving a tapestry of reality through a series of temporal negotiations.
All of these interpretations, however, from Copenhagen to many worlds to the transactional model, rest upon a foundational assumption that is so deeply ingrained in the practice of science that it is almost never questioned: the freedom of the experimenter to choose what to measure. The validity of Bell's theorem, which proves the impossibility of a classical local reality, hinges on the premise that the settings of the detectors in an experiment are statistically independent of the properties of the particles being measured. A final, deeply unconventional perspective, known as superdeterminism, proposes that this very assumption is the source of all of quantum mechanics' apparent paradoxes. Superdeterminism is the radical idea that there are no truly free variables in the universe. The state of every particle, every detector, and indeed every experimenter's brain was precisely determined by the initial conditions of the universe at the Big Bang. In a superdeterministic universe, when an experimenter decides to orient a polarizer to measure the spin of an electron, that choice was not a free one. The specific configuration of atoms in their brain that led to that choice was inextricably linked through an unbroken causal chain stretching back billions of years to the specific hidden properties of the electron they are about to measure. The particle and the measuring device are not independent systems that meet for the first time in the lab. They are part of a single, indivisible, and intricately correlated reality. They are like two characters in a novel who believe they are making choices, but whose actions have already been written and are merely unfolding according to a pre-existing script. This profound correlation between the measurement settings and the system's hidden state is precisely what is needed to violate Bell's inequalities without resorting to faster-than-light influences. The appearance of non-locality is an illusion, created by our mistaken belief that we are ever asking the universe an unbiased question.
This viewpoint is often met with strong resistance, as it seems to deny free will and invoke a kind of cosmic conspiracy, where nature precisely arranges things to fool us into thinking quantum mechanics is strange. Its critics argue that it renders science itself impossible, for if we cannot freely choose our experimental conditions, we can never be sure we are conducting a fair test of any hypothesis. However, proponents, including the Nobel laureate Gerard Tufte, argue that it is a logically coherent possibility that is being dismissed too quickly on purely philosophical or aesthetic grounds. They contend that our intuitive notions of free will and statistical independence may simply be artifacts of our macroscopic perspective and not fundamental features of the universe. For those who prioritize determinism and locality above all else, superdeterminism offers a potential, albeit costly, path back to a classical-style reality. It suggests that the strangeness of the quantum world is not in the world itself, but in our flawed assumption that we stand apart from it as independent interrogators. It proposes that we are not observers of a cosmic play, but fully determined actors within it, and the script we are following was written into the fabric of spacetime from the very first moment of existence. This reframing of the universe as a singular, correlated whole represents the most extreme attempt to preserve a classical conception of causality, but it is far from the only modern effort to dissolve the paradoxes by rethinking the fundamental relationship between the observer and the observed. A profoundly different approach, which has gained significant traction in recent decades, is known as quantum Bayesianism, or cubism. This interpretation proposes that the central error in nearly a century of debate has been the assumption that the wave function represents a direct objective property of a physical system. Cubism argues instead that the wave function is purely epistemic. That is, it does not describe the world as it is, but rather it represents the state of knowledge, the degrees of belief that a particular agent has about the probable outcomes of their future interactions with the world.
In this view, quantum mechanics is not a theory about how physical reality behaves in our absence, but is instead a user's manual for any agent navigating the universe that is fundamentally indeterministic. The probabilities encoded in the wave function are not objective chances, like the 50-50 probability of a classical coin flip, but are instead subjective Bayesian probabilities, quantifying an agent's personal degree of belief in a future event. When you or I assign a wave function to an electron, we are not describing the electron itself. We are summarizing our own unique set of beliefs about what we will experience if we choose to perform a measurement on that electron. The act of measurement, then, is not some mysterious physical process that collapses an objective reality. It is simply an action an agent takes that yields a specific personal experience. Upon having that experience, for instance, seeing a flash on a screen at a particular location, the agent updates their beliefs about the system, and consequently, they update the wave function they use to predict future experiences.
The infamous measurement problem, from the perspective of cubism, simply dissolves. There is no abrupt collapse of a physical wave, because the wave was never a physical entity to begin with. There is only the continuous and natural process of an agent updating their beliefs in light of new evidence, a process familiar to us in every other aspect of life. The strangeness of quantum mechanics is not that the world is objectively weird, but that the rules for updating our beliefs about it are different from what our classical intuition would suggest. Cubism remains quiet on the ultimate nature of the reality that gives rise to our experiences. It claims that quantum theory itself does not provide that description. The theory is about the interplay between the agent and the system, the interface where knowledge is gained. It suggests that reality is not something to be passively viewed from a distance, but something that is co-created in every interaction, with each measurement adding a new, irreducible fact to the world from the personal perspective of the agent who made it. A closely related, though distinct, philosophical framework is the relational quantum mechanics developed by the physicist Carlo Rovelli. Like cubism, this interpretation denies that a quantum system has any absolute observer-independent properties. However, it goes a step further by removing the special status of the conscious agent or observer. In relational quantum mechanics, any physical system can be considered an observer relative to any other physical system. The state of a particle is only defined in relation to the system with which it is interacting. An electron does not have a definite spin in and of itself.
It only has a definite spin relative to the measuring apparatus that detects it, or relative to a photon that scatters off it. The universe, in this view, is not a collection of objects with pre-existing properties, but rather a vast and intricate network of relations.
The description of the world is thus fragmented into a multitude of perspectives. There is no single true story of the universe, no absolute view from nowhere. There is only the state of System A relative to System B, and the state of System B relative to System C, and so on. A physical event is the establishment of a fact, an interaction that actualizes a property of one system in relation to another. Before this interaction, the properties were merely potential. This means that my description of the world, based on my interactions, can be different from your description of the world. For instance, from my perspective, the measurement of Schrödinger's cat has already occurred, and the cat is definitively either alive or dead. But for someone outside the sealed laboratory who has not yet interacted with it, the cat and I are both part of a single large quantum system that remains in a superposition until they open the box and establish a new set of relations with it.
The apparent contradiction is resolved by understanding that all state descriptions are indexical. They are always tied to a particular perspective. The consistency of our shared reality emerges not from a single underlying truth, but from the coherence of the information exchanged within this network of relations. When I tell you that I found the cat to be alive, our systems interact, and this interaction establishes a new fact that now becomes part of your relational description of the world. We build a consensus reality, piece by piece, through these physical interactions, communicating information across the network. The objective world of classical physics is therefore an emergent approximation, a description that holds true for a community of observers who share a large history of consistent interactions. Reality is not a static substance, but a dynamic and shimmering web of perspectives, where the only concrete facts are the fleeting moments of interaction that bind the universe together.
We have journeyed through a remarkable landscape of ideas, each an attempt to make sense of the same set of experimental results and the same elegant mathematical formalism. We began with the pragmatic Copenhagen interpretation, which walled off the quantum world from our classical intuition with a veil of irreducible uncertainty. We explored the breathtaking scope of the many worlds interpretation, which populates the cosmos with an infinity of parallel universes to preserve the universal validity of the quantum equations. We considered the hidden guidance of Bohmian mechanics, which restores a classical-like determinism at the cost of a deeply non-local reality. We saw how quantum Darwinism seeks to explain the emergence of our solid, objective world from the selective proliferation of robust quantum information within the environment. We pondered the transactional interpretation's dialogue across time, where reality is a completed handshake between the past and the future. We confronted the profound challenge of superdeterminism, which saves locality by tethering our every choice to the initial moment of the Big Bang. And finally, we have seen how cubism and relational quantum mechanics attempt to resolve the paradoxes by relativizing reality itself, grounding it not in objects, but in information, belief, and the relationships between systems.
What is perhaps most striking about this grand tour is the profound lack of consensus. After more than a century of investigation, the very meaning of our most successful physical theory remains the subject of deep and passionate debate. This is not a failure of science, but a testament to the depth of the questions that quantum mechanics forces us to ask. The theory works with unparalleled precision, yet the nature of the reality it describes remains elusive, shrouded in a conceptual fog. It seems to resist any single, comfortable narrative, challenging the very language and philosophical presuppositions we have inherited from our macroscopic world. Each interpretation offers a complete, internally consistent worldview, yet choosing between them seems to depend as much on philosophical taste and metaphysical inclination as on empirical evidence.
Perhaps the ultimate lesson of the quantum is one of humility. It may be that the universe is not designed to be intuitive to minds that evolved to navigate a world of medium-sized objects at medium speeds. The search for a single definitive story of reality may be a category error, a projection of our own narrative desires onto a cosmos that operates on a different logic entirely. The quantum world is not a riddle to be solved, but a new kind of grammar to be learned, one that describes a world of potentiality, context, and relation. And so, as we reflect on these quantum echoes, we are not left with a final answer, but with a richer sense of possibility. We are left with the quiet and enduring wonder of a universe that, the more we learn about it, proves itself to be not only stranger than we imagine, but stranger than we can imagine. The inquiry continues, not in a frantic race for a solution, but in a calm and steady appreciation for the profound and beautiful mystery that lies at the very heart of what is real.